Welcome to Building Recursive Workflows in Broadway.ai. It's a joke. Please, it's going to be a few of those, so if I could get the applause line, that'd be great. I'm Anthony Accomazzo. I'm one of the co-founders of Sequin. I'm joined here by two of our stalwart engineers. We got Randy and Bucky over there. So if you have any complaints at the end of this talk, please direct it towards them. Yeah, complain right now if you want to. So today I'm going to talk through how we scaled and re-architected one of our core systems at Sequin. And we'll start by talking about the problem space. Then we'll talk about Broadway at a high level. Who here has used Broadway before? Yeah? Okay. Oh, a lot of you. Okay. So there's going to be some basics for those that haven't, but then we'll get into some good meaty advanced stuff too. So I hope everyone will get something out of this. We'll then discuss pipeline design and some decisions that we made and some optimizations that we made as well that helped our pipeline run really fast. So to understand the talk, you'll have to understand a little bit about Sequin and what we do. So we take tables from the different SaaS services that you use, like Stripe or Shopify or Salesforce, and put them in your Postgres database. So now you can use Ecto to read from your tables. And then if you do inserts, updates, or deletes, we'll actually capture those, write them to the API first. If it succeeds validation, we'll commit it to the database. Otherwise, we'll roll it back and return to you the API error as a Postgres error. So that part where we capture the write, we just shipped back in July. It's like totally bananas. One of those things that I can't imagine doing in any other platform other than Elixir, but we'll save that for another ElixirConf talk. For today, we're going to talk about that system that gets that API data and puts it into the database. So when we think about the data pipelines, we normally think about something like this, right? Where we have a bunch of different workflows or workers or live view or controllers, and they're throwing stuff into a queue, and then we have workers that are pulling stuff off of that queue to process them. But what about web scraping? In web scraping, you make a request to grab some page, it comes back with a bunch of different links, and now you have your next set of work, 20 links to go chase down. So then the next generation, you follow those pages to grab those. And you're kind of reducing over work, and each generation produces the next generation of work. And so API scraping, which is just white-collar web scraping, is exactly the same way, right? Where you make an API request, you come back with a cursor, and that cursor is going to be that next job for you to do. So the way I think about it is like this, where you have a manager with a job, it gets passed down to a worker. When that job's completed, it produces the next job in your pipeline. And so this is what ChatGPT calls a recursive workflow. And this phrase was nowhere on the internet. I don't know where I came up with this, but all of you decided to attend a talk that was named by an LLM. So joke's on you. Now, when we think about the requirements that we had going into this, our requirements were that it was really fast. We want it so that when a change happens in the API, it shows up in the database very shortly afterwards. And it really needs to be high throughput and highly concurrent. So we could have millions of these jobs coming through the pipeline in a day for just one sync, because each job is very small and it's a single request to an API endpoint. So back when we started building Sequin, I wasn't an Elixir Pro. Here I am right after I committed my first line of Sequin code. That's obviously Bill Gates. And I'd never been to an Elixir conference. And in those days, we still had to write our own code. So we went with the simplest implementation possible, which is it's just Gen server's pipeline. And so you have a manager acting as, a Gen server acting as your manager, and then worker Gen servers pulling from that manager. And this is what it looks like. So relatively simple. You bootstrap it with those endpoints because, again, you're not pulling your work from anywhere. That work is all internal. You turn that into a job queue. And then if a worker calls to get some jobs and there's nothing in the queue, you can reply with nothing. Otherwise, you can pop a job and return it to your worker. And you really want to do a polling system as opposed to a pushing system. It's just way easier to implement. So here we have a worker just on a timeout every 50 milliseconds pulling work. And if there's no work to do, it just re-enqueues to do that again. Otherwise, it goes off and runs the job. So this actually works surprisingly well. And just with this pipeline, you already have something that's months ahead of what you do in another programming platform. There's a few problems with them. None of them are major, but to make this work really well in production, I'll name a few of the things that we were running into. So one is that shutdown is pretty messy, right? You kill the pipeline and everything just sort of collapses. There's no grace period. Jobs are fire and forget. So if a worker dies, it can't produce its next successor. And you also have some issues when you're pulling for work super frequently. So we didn't really have the problem of like hungry workers DOSing the manager. It was more that we would have them die when they were in the middle of calling the manager, which just meant a lot of logs were spewing everywhere. So it's really messy in test. So we were looking to fix these problems and other ones that we were running into. And as we were doing that, we were wondering what else we could use out there instead, and that's when we found Broadway. And the way I would kind of think about Broadway in terms of like layers of abstraction, this slide might be helpful, is like the very bottom is obviously the low level of a process that you might spawn, and Broadway is a slightly higher level than GenStage in an abstraction. And the way I like to think about it is that GenStage gives us the basic primitive for how a producer gives work to consumers. So it takes care of all the wiring, which is quite nice. And then Broadway, one layer up, gives us some more nice features that are really good for data pipelines. So things like acknowledgments and graceful shutdowns. We won't have time to talk about batching, but it allows for batching as well. So acknowledgments are how, when a job flows through the pipeline, we want to produce the successor to that job. So we've fetched one page of an endpoint. We want to fetch the next one. Acknowledgments are how we go back to the beginning with that job to the producer. And if it fails, we also want to let the producer determine what to do next. Do we throttle this pipeline? Do we retry it? What have you. Graceful shutdowns are nice. We can signal we want to take the pipeline down, and all the workers are given time to finish their work before they're terminated. But maybe the best part about adopting Broadway, as with any library, is it gave us some standards and constraints. So it prevented us from pulling out some footguns, which we'll talk about in a little bit. Also meant that we can hire new people onto the team, and they can learn about our data pipeline relatively easily by just reading the Broadway docs. One benefit that you get from Broadway is you can go pick up off-the-shelf producers. So if you are doing a traditional data pipeline with a message queue, you can find a producer on HexPM, you can plug it in, and you're off to the races. I mean, a lot of you have experienced this. You just configure Broadway with some parameters about your SQS queue. Here's the queue URL, here's my API key. And then you write one function, which is the handle message function, and this is what is invoked by your workers every time they have a new SQS message. So all the lifecycle around pulling messages from SQS, what to do about acknowledging them, retries, failures, is taken care of for you, and all you have to do is implement this domain code on how to handle the message there. But for us, and for the workflow and the job engine we're talking about, we're not using a message queue. So we're going to build our own producer in order to handle the workflow. So these are kind of the different steps we'll go through in the pipeline. The data structures we'll use, just keeping it super simple. We use a bunch of different structs to basically create all of our different jobs in our system. So here's a very simple one, just describes an endpoint we want to pull and a cursor we can use for that endpoint. And then we wrap that in a Broadway message, which is what Broadway has you use to pass messages down the pipeline. So here's an example of some producer code. We don't have time today to talk about demand, but basically those handle demand functions are how workers ask for work to do. And one of our requirements is they only ask for one job at a time, which is why that first parameter there is 1. Again, if there's nothing to do, don't give them work. We can see there in the second element of the tuples, that's how we pass messages from the producer down to the workers, is by including them in that list there, is that second element in the tuple. So you can see in the second handle demand, we have some work to do, so we can go ahead and pop it off for the worker to do. And as we saw before in that simple SQS implementation, we implement one function for our workers to handle the message. And so we can do all of our stuff in here. So API upsert, parse it, database upsert, and then we update the job with data that we'll need to determine the successor job. So one API call could end up resulting in 10 new API calls after that to fan out and grab other objects. And we'll see later how that happens. But this is an area where we can sort of update that message with new data. If the message fails, if it raises, it'll still get acknowledged as a failure, which is nice. We can also mark it as a failed message right here. And then that'll be what comes back to our acknowledger. So in a Broadway message, you can see that acknowledger key. We tell Broadway who's going to do the acknowledging. Here we say it's in our producer module. We can put it wherever we want. And then briefly, this is what the acknowledgement looks like. So the important part here is just that we're going back to the producer with this job and letting the producer decide what to do next, because it's the one that's in charge of determining what successor jobs are going to be produced in the pipeline. So this is what that looks like. We're back in the producer. It's handling a completed job. And depending on if there's new jobs or not, we can produce new jobs right away for the pipeline to consume. Okay, so that's Broadway at a high level with a custom producer. Let's talk a little bit about the design of this pipeline. There are 2 stages in this example and what we're doing at Sequin. We have the API request and then the database upsert. And you might be tempted to think, well, I can have one worker do my API request and another worker do my database upsert. And I call this temptation the factory worker anti-pattern. And it's that you're thinking about a factory line and how each worker has a specialty and they should all kind of have one job. But of course, as you might know, Elixir processes can all run your code equally well. And the way we should actually separate our business logic in Elixir is with modules and not with processes. Processes are how we model concurrency, or we might manage state. So this is what it looks like to model your workflow using processes, and this is what it looks like to model it using modules. So we have one process executing the code. They're both pipelines. One is just with different processes, and one with modules. And I think what was really helpful for me was this thinking about OTP applications and processes is basically falling into one of 2 buckets. And those buckets are manager processes and worker processes, or coordinators and executors, or a really fun analogy I like is managers versus makers. So you guys familiar with the Paul Graham essay of manager schedule, maker schedule? Who's read that essay before or heard of it? Okay, yeah, a few of you. So a manager schedule is full of meetings. It would give most of us a heart attack. They're very interrupt-driven. They have to be very responsive to their teammates. And of course, a maker should be allowed to go off and work on whatever they need to without interruption, or at least in theory. So managers in your applications likely have a lot of handle calls, and they should be as responsive as possible. If they're not responsive, they're very likely going to become a bottleneck as you scale. Conversely, makers should be allowed to go do their thing uninterrupted, and if you try to call the maker processes or the worker processes, they could also become a bottleneck. So it's really important that we divide our work between managers and workers and not necessarily between workers. That's usually the wrong layer to be thinking at. So after we embraced this design principle, embraced Broadway, we began scaling it up, and we're running many Broadway pipelines, and it became time for us to begin optimizing. So I'll talk about a few of the fun optimizations that we made. So the first one is a very simple one, and that is to keep acknowledgments relatively light in the producer. So again, as we just talked about, that manager process, the producer process, should be as responsive as possible. So we want to execute very little code in there if we can. So moving a lot of that acknowledgement into the worker and having the producer basically just in charge of fanning out jobs to the next worker. But the next one's really fun. And this one will apply whether or not you're using Broadway. So in Elixir, when you send a message from one process to another, all the contents of that message are effectively copied into the process memory of the receiving process, right? Because every process has its own heap. So we have this very big data structure that describes the full schema of the Postgres database that we're syncing to. And sometimes this thing can get up to like a megabyte or two. And we were sending it along with in our Broadway messages. And so if you can just imagine, we have this big data structure and we're copying it from producer process to worker process, back to producer, back to worker, back to producer. And it was crazy. Basically, your memory is going to be super high because your garbage collector can never keep up. Your CPU is going to be high because you're garbage collecting all the time. And then there's an overhead because you have to copy this message over and over again every time you send it. So my tip there is to keep the messages small. And what we basically did was, a worker process is brought up, is you might know you can't really manage, there's no like state in these worker processes. So we actually used the process key value store. It was a great use case for this. So when a worker first comes up, it's totally green, and then it processes its first message. And down there in load big struct, you can see that we use the process key value store to try to see if we already have it in memory. If we don't, then we load it, we put it in our key value store, and then we have it. And so future messages, we don't have to load it again. And note that you can't, ETS is not a solution for this, like it has to be in the process. And so the process key value store is the way to go here. The last optimization I'll mention, so normally in a job processing pipeline, the limiting factor is CPU. But that's not the case for API scraping. Can anyone tell me what the limiting factor in API polling or scraping is? Not network. Close. It's very unfun. Yeah, throttling basically. It's rate limit. So rate limit is actually the limiting factor for pretty much every API. And every API we work with has its own beautiful rate limit algorithm that we've never seen before that we have to work with. And so no matter how concurrent we make our job pipeline, the rate limit's actually the thing that will always be stopping us. So Broadway's rate limiter wasn't sophisticated enough for our use case. You can basically say, here's an interval, here's the amount of requests I can make in that interval. So for us instead, we have something like this, and I think the best way to think about this mental model is, in the Erlang VM, you basically have work that you want to do, and if you can't do the work right now, it goes into the run queue, and then you have a scheduler determine when it can see the CPU, like when it has some time on the CPU. For us, it's actually, instead of a CPU, it's the API that we're concerned about. And so we have this scheduler, which is just a module, and that module determines which one of our jobs will get some time on a worker and then therefore on the API to actually do its thing. And the cool part is we can actually make that scheduler very sophisticated. So ours takes into account how busy the API endpoint is, how behind we are, if this is an important API endpoint, and uses that to prioritize work and determines when we produce jobs into the queue. The last thing I want to mention, you just want to take a step back and consider what would this all have looked like without Broadway. At the end of the day, Broadway is not a very big library, and this is very common with Elixir libraries, is a lot of them are actually pretty thin, and it's because you can build relatively robust abstractions with the big building blocks of OTP pretty easily. But that's almost a paradox. It's like because these libraries are so simple to understand, you can pop the hood open and see how it works, that makes you almost more willing to adopt them. And the inverse paradox also exists in other programming languages, not naming names. They have like 6 different ways to do concurrency, 3 different syntaxes, and a new execution runtime every quarter. And when you're in that environment, you almost need libraries even more because it's so hard to do these things yourself. But then you adopt a library, it's inscrutable, you pop the hood open, and you're seeing JavaScript you've never, you're seeing a programming language you've never seen before. The neat part is that we can start with Broadway, and if eventually our needs force us out of it, it won't be difficult at all for us to convert this to a gen stage pipeline, and then we can always go back to gen servers if we have to, where it all started. So with OTP, while the primitives can feel like magic, it's very cool that putting them together doesn't feel that way. That's all I have. Thank you.